so I can see
Sure, sure,
how we
sure,
can
sure.
proceed.
Let me. Okay, uh, where it goes. Okay. So I guess maybe I can start a bit about my experimental work, which is about the InnoSLAB laser. I should introduce these things to you people as well. Just
Sure,
a hint of its configuration and other things.
sure,
Okay.
sure.
Okay. So where is okay, so this is I have a presentation before, so like let's start. I hope you can see this the presentation here. Can you see it?
Yes, yes.
Okay. So let me go to which slide I have prepared on.
Can you please make it full screen?
Yeah, just a minute.
Yeah.
Uh, Okay, so as if like you people are familiar with the solid state lasers, so in solid state lasers mostly the gain mediums is have like different kind of shape. Okay, very traditionally the laser medium is like used to be the rod shaped lasers. I placed it fiber because it's also like a type of a solid state laser as well, but not a free space one. So whatever the laser we talk about, like we have like two main things to consider. Like it must have like large surface to volume ratio, and like some things like it can support high power as well as high peak power can support as well. So over the time, three configurations have been like the rod lasers, okay, slab lasers and the thin disk laser. These both lasers this technology, the slab and thin disk, they appeared like in 90s, 45, 44, all together one after another. You know, both belongs to Germany. So in the slab laser, which particular I will talk about, basically it's a rectangular slab medium. Okay, so it's two surfaces like the top one, the last surfaces are like not polished, nothing else. They are just used to for the heat extraction connected to the heat sinks. And these two surfaces, like the small dimension surface along the width, they are like used for the end pumping as well as for the lasing system. So
So what are the dimensions actually?
okay. Uh, Basically, this is the rectangular shape slab crystal. Okay. So dimensions vary. It's not a particular vary. It can be like you can. This is like here is the dimension of a slab crystal. A, B, C. A is like it's the width of a crystal. B is the length of a crystal. Okay. Other way around. You can say A is the length of a crystal along the horizontal. Okay, along the x-axis. You can say B is the width, optical axis width. Okay, along the Z, whatever we call it, is the optical axis width, and C is the thickness of a slab laser. So generally, this the length of a slab crystal is varies from 10 to 15, 20 millimeter even. Some papers have reported they have used 40 millimeter long, wide this crystal. The width is about 10. Okay, 14 by 10, and thickness is mostly 1 mm, but somewhere it can be used at 1.5. So big advantages like this small thickness, it allows us to extract the heat very efficiently. So as I told, it's a rectangular shape. It is partially end pumped crystal, which is pumped from one side. Like one-sided, it can be pumped from both sides, but like it end pumped crystal. And here, the main thing is like here, when we are pumping this crystal, we don't fill the full phase of this crystal. Like the A, if A is the pumping phase, we don't fill it with the completely with the pump beam. Rather, we just fill it partially at the middle of this side. So that's why it is called as partially end pump. It is like a end pump slab laser as well, because it is partially pumped by a laser diode, stack of laser diode, which has been shaped with the different systems in to match the geometry of a slab crystal. So So this is all about how the crystal, the dimensions of crystal. The last here you see we have just configuration, a stack of diode lasers. It's a vertical. It can be a vertical stack, horizontal stack, whatever it is. The output of diode laser has to be shaped to match the this crystal profile. So it is shaped by a different, like the cylindrical lenses into a sheet, like almost which covers all this crystal, the length of this all crystal, uh, the A face along the x-axis, it completely fills it. But along the y-axis, that is this thickness, it only partially fills at the middle. Just like example, if the thickness is 1 mm, so the pump beam has to be like 0.5 mm thickness. So it fills it in the to have this, it can be like 0.6, but depending upon the, then again, the threshold or other things got affected. So in InnoSLAB amplifier, basically what happens, we definitely have an amplifier section and a seed oscillators. In amplifier section, this the crystal is like pumped with a stack of diode lasers again, and the seed lasers, uh, which is also the output of seed lasers matched to mode match along the vertical direction to the pump say pumping mode, because the what we say, uh, if like we have a 0.5 mm of thickness of pumping system, let the pump mode size is 0.5 mm, the output of a crystal along the vertical direction also is turned into 0.5 mm. Now, one of the important thing of InnoSLAB laser to be discussed, that the cavity configuration. Normally, the cavity configuration in InnoSLAB, or whatever the slab laser, lasers we consider as say stable laser configuration. But InnoSLAB use the hybrid laser cavity configuration, where in the one dimension it remains as the stable one. That is, in the one dimension, the mode size doesn't change. It kept the same whatever injected inside, while the another direction, it is unstable, where the mode size can be like tailored with the type of the input and output mirrors. So rectangular slab crystal, laser diode and pumped, hybrid resonator, configuration of arrangement of two cylindrical concave convex mirrors. There have been used, it can be concave convex mirror, it can be a plane convex mirror, it can be a plane mirrors. But the point is to have a good beam quality. If in the slab crystal, if we use a stable resonator, we wouldn't have a good beam quality, because the output profile will match the profile of a slab crystal. So in the horizontal direction, we most likely will have a rectangular type of output. So here, once we have an amplifier setup with a hybrid resonator cavity, the seed lasers comes, which is reflected to take multiple pass through the slab, pumped slab crystal to get amplified. This passes can be configured depending upon your requirement, output power, and the pumping power as well. So here it can be in each pass, in this slab crystal, in each pass, the seed size remains same along the horizontal direction, but its output, its beam gets supplied in along the vertical direction. I think I will have a if it is, yeah, here the configuration like we have for the amplifier section. Here we have a laser diode. This is the pump shaping system. These are the two cylindrical lenses. The waveguide. Waveguide is used to homogenize the laser the pump beam. Cylindrical lens again to shape in one dimension. The spherical lens so that it can be matched to the laser crystal. So here you see the laser crystal, like this is the dimension I have shown is the x-axis. Okay, so it completely filled along almost over 95% of this slab crystal along the horizontal direction. So here we have an input mirror, which generally, traditionally is the concave mirror to bring the divergence along with the output mirror to the seed beams. So for the amplifier sections, what I am talking about the amplifier section here, what we have done, like we collimated the beam, we reshaped and collimated along the vertical direction, so its mode size doesn't change too much along the vertical directions. Again, for the reflections, this is the input mirror for the reflections. What I'm talking about is my configuration, which we used. But generally here you can just put one mirror where just one mirror at this place to reflect the seed lasers to the slab crystals. But I use one discrete mirror for each pass to the slab crystal. So you can see at every pass, the slab crystal, when the beam passes to the slab, it get expanded. So this brings the advantage, like as the size increases, it extracts more energy, as well as the intensity remains low. So we wouldn't have any damage occur to the crystal. Second, we wouldn't have any the nonlinear effect that will be not very prominent, which are very important for the high power laser systems. When we especially talk about the femtosecond to the kilowatt level laser systems. So in every pass, the beam get diverged in the horizontal direction, it expanded and allow us to extract more power, and the intensity remains the same. So output profile we have, like with the InnoSLAB lasers, we can with the single end pump, we can reach up to like 200, 300, even a 500 watt of power with the picosecond laser. With the femtosecond lasers, people have achieved it, but then the nonlinear effects comes in the play a bit. But mostly, slab lasers, like with the moderate gain and moderate nonlinear effect, it lies between two extremes. One, we have a fiber lasers, which have its own advantage of high gain. Another, we have a thin disk lasers, which is like the gain is very low, single pass gain I'm talking about. But like the thin disk lasers, the non-linearities are very low, while in the fiber laser non-linearities are very high. But the this slab lasers comes between both of these technologies. Like it offers the moderate gain per pass, it offers very moderate non-linearities. So that systems can be like build up with stable output up to like 300 to 400 watt of power with the picosecond, and like few hundred watt with the femtosecond system. Although the people have like built up with the 1 kilowatt level system, but they cascaded it with the power amplifier, second stage amplifier. So I think this is all about my InnoSLAB configuration, which I just want to let you know. The experimental thing we will talk about at the moment about our experimental process. Experimental work here, what we have done. But I just want to let you know about the InnoSLAB lasers. Second thing is important, which I want to share with you, is the shaping system for this InnoSLAB laser system, because this shaping system is pump shaping system is important for InnoSLAB lasers. In horizontal direction, it has to be homogenized, fully homogenized pump beam. Otherwise, if it is not homogenized, it will have a bring the bad beam quality. It will affect the gain, and thirdly, it will like definitely introduce some thermal effects, which again disturb the mode matching system of mode matching of the output beam. So for the laser diode, as we know that the output of a laser diode is also like we have if it is not collimated along the x-axis, y-axis, it doesn't have the fast axis collimations and slow axis collimations, then the divergence and then the output profile of the laser diode also follows the rectangular shape. So that's why it is like ideal case where we can also have a geometry which also match the profile of the laser diode. So in here, what I want to say, like we need to shape a laser diode which has a beam profile with a top head distribution along the slow axis. That is slow axis which we call attached with the laser diode. This is generally the x-axis, and Gaussian beam profile along the fast axis. So this is the motive for the shaping system of a laser. What I have for just for you people who are like not familiar, because I was also learning about how to do the shaping system with the ZEMAX laser diode, laser diode to shape its output via ZEMAX and use it for the pumping of our InnoSLAB lasers. So I was like, I made slides where we can like it kind of a tutorial for you peoples, especially like if Mudassar, because he know a lot about ZEMAX, and if given these things to him, he can more understand and we can discuss as well. So I have just like, to my understanding, how to configure a laser diode in a non-sequential mode, non-sequential mode of VMAX. To my understanding, I have built like with an example that if we have a laser diode with a single bar, okay, single bar laser diode. As you all know, the each bar of a laser diode is based on different emitters, and each emitters have its own dimensions, and they have the pitch of emitters. We have like the spacing between emitters. Sometimes this spacing is like from the center to center. Correct me if I am wrong. Sometimes like it is quoted the spacing from the edge to edge of a emitter. So like to simulate laser diode source via ZEMAX, the major point is like how we input the parameters in the ZEMAX. Okay, because like ZEMAX will have different parameters. The first, if we select a source diode, you might all people familiar with these window bars coming here, like it have X position, Y position, tilt about X, tilt about Y, Z, material, layout, and analysis. This is like common of these all parameters. Next, like it appears astigmatism, X divergence, X super Gauss, Y divergence, Y super Gauss. Yeah, number X, number Y, delta X, delta Y, X width, X sigma, X width half, HX, X width, sigma, Y sigma, and Y width, HY. Okay. Most of them, I got like knowledge of this, what are they meant to be. But some of this, like I'm still confused, like X width, HX, and Y width, HX, like what does that represent? Is it like when we configure the laser diode source and we see the output, and then we bring these values here, or we have these values before? Because the data sheets don't provide these values. The data sheet of laser diode never provided these values anywhere I have seen. So to start with just an example, like we have a laser diode bar. Okay, as I told, it has emitters in the bar, which is separated by some space. Whatever the spacing between them, it has been like given in the data sheet, or we have to extract from the other information which are given, like the total pitch of system and the width of the output beam, if the given is if it's given, so we can calculate this. So like if we have a one bar with volume configuration, total emitter 19 linearly arranged horizontally along the slow axis. That is x-axis. Spacing is 0.5. Size of each emitter 100 into 1 micrometer. So 100 is also a micrometer. Okay, width into thickness. Fast axis divergence is full angle 30 and slow axis divergence is 15. So it's like fast axis divergence it means like this one is without fast axis collimated lenses. Otherwise, if the fast axis collimated lenses are being used, this divergence is like much lower than the this value. So this is the initial we have.
Okay, so Fiasa, so Mudassar, I mean, probably you can comment here. Mudassar and Nabil. And you can ask the question to Fiasa, I mean, if you, both of you.
There is like two things is maybe it get a bit long, but I don't want to get it long. I can share these slides with them. They
No,
can
okay,
understand.
Just a minute, Fiasa. That's okay, but maybe if they have any question regarding this one,
Sure.
Otherwise it can be shared later on, no problem.
Yeah, sure.
So Mudassar and Nabil, your mic I think is mute. Yeah.
Sorry. Thank you. So Fayad, I just want to first little bit clarify the system. Like you sticking diodes, you are pumping a crystal, and you then throwing a femtosecond seed beam, and then it passes through it. What do you want with that? You want to diverge that beam or what? I'm just little bit curious about that, like this system.
Okay. Let me tell you. Okay.
Yeah, this one.
Where is the animations? Here it's coming.
Yeah, this one is fine.
Okay, so if you people are very much familiar with the laser diode systems, so not laser diode system, laser system, as Tayyab is, I'm sure he knows all this thing about. So that's why I didn't go in much depth to explain all about the laser system.
No,
And you
probably they
people
are
most
not very
likely-
much, I mean, they don't know to that extent. So, but
Oh,
they know definitely,
so,
but to that.
so accept my apology, because I was just like giving it our look of this system.
No, but
So
it's okay.
No,
When,
it's okay.
yeah, because it's
It is
okay at the
totally
moment
fine.
because time is also, we don't have much. So
Yeah,
we better to stick.
I'm just asking. I just want to
Okay.
ask, like laser diode, you shape the beam, then you just fall into a laser crystal, whatever it pump the laser crystal, and then you throw a seed beam, and you say it's be like in an animation. I can see its width is increasing, whatever the axis is.
Yeah.
What was the purpose for that? If you have a seed beam, you just passing through a crystal which is pumped with some laser diode, shaping is a different system. What do you basically want to do with that seed beam? Whether you want to just diverge it or you want to amplify it? I'm little bit confused in that.
That's okay. That's basically Mudassar, what we are like in the laser system. There are two things to talk about. Like one is the CW laser system or the pulse laser systems. Okay.
Yes.
When we talk about the laser systems, we have a single system which is not amplifier. We call it mostly the oscillator. Okay. When we
Yes,
talk
yes.
about the pulse systems. Okay. It is like it generates the pulses according to the configuration. It can be mode locked, it can be like Q switched, whatever it is. Okay, but in that system we cannot amplify, get enough power. Like we cannot take it to the like multi-hundred of watt level systems. So for this we introduced an amplifier system where we have already a seed laser, which power is like very much small, like maybe 5 watt, 10 watt, maybe milliwatt. Then we amplify through a amplifier system, which is basically this here. I am showing here is all a complete amplifier system. Like in overall configuration, there are a lot of different amplifiers, thin disk, fiber amplifiers, or others. In particular, this case, this is the laser crystal. Whichever the laser crystal, YB YAG and YAG, whatever. This crystal is pumped to have like population inversion. Okay. This is pumped by the stack of diode laser. Okay. And this laser diode is shaped to have this pumping systems. Okay. Now the seed lasers, our motive is to get high power. Okay, it's not about the divergence, it's nothing else. Like
Mhm.
if we have a seed laser, a 5 watt, we can at the end can increase this output beam. Like if this beam is coming off 5 watt, okay, let's say
Mhm.
just okay,
Okay.
when it passes through laser crystal, okay,
Mhm.
multiple times, in every time it get amplified, it get gain, and it like all the population inverted population, out of this it extracted the power from each pass and then
Okay.
amplified to higher level. Okay, at
Okay.
the output we may have like 100 of watt, we may have 200 depending upon our configuration. Okay,
Okay.
so this seed lasers cannot solely provide this much of power. Like whatever we can do, this there are like deficiencies, apart from the thin disk oscillators, there is not a single system which can provide 100 or multi-hundred watt of a pulse laser directly without amplification. Okay,
Yeah, I
this is
understand. It's like
okay.
amplifier. You just taking a 4-pass amplifier and then you amplifying in the divergence is. I think you are diverging the beam like in animation, so that's why I understand.
No.
Like
Basically,
you are
what I'm showing is
amplifying,
not diverging. It's basically taking,
increasing power.
making it to pass through the system. And this
Mm.
particular configuration for this slab crystal, because in each pass, the beam get diverged by the magnification of these two lenses. Like this is our first, the big one is like input mirror, maybe like let's say it's
Yeah,
a
yeah.
500. Its radius is 500. This is the convex mirror. Its radius, let's say, is like 350. So their
Okay.
magnification power will be like about 1.5 or 7. So
Yeah.
whatever the beam size will be here, it get magnified with this magnification in each pass of okay,
Okay.
1.75 times it magnified in one pass. If we use the same mirror, it will
Mm.
like 1.75 times second pass. If we use like smaller one, it will have more higher magnifications. So in each
Yeah.
magnification, like because in the lasers, you have to manage the nonlinear effect. So this beam spreading is important to manage the non because if the size remains same, you will have the
Mm.
nonlinear effect. You could have the nonlinearity second order, third order,
Yes.
nonlinearities appears with the smaller beam size. So that's why we
Okay.
must have to induce the uh, divergence in this beam to
Okay.
expand it in every
Now I
pass.
get it.
Okay.
Now I get it. Okay. So you
Okay.
want to simulate this pumping system basically using ZEMAX just to show
Yes,
the laser
basically.
system.
This ZEMAX
Yeah.
is like can be used for like if I want to shape the seed lasers,
Mm.
whatever the seed beam laser beam I have to shape it before injecting. ZEMAX must be used here, can be used here, but for this shaping system, ZEMAX must be used.
Okay, so you want to just we want to shape this like a beam shaping optics we want to simulate.
Exactly. We want to
Okay, I
simulate.
understand. Okay.
and
So
and then it's like
mhm,
as I told before, like if you people has get the NCs as well. So with this input parameters, we can directly calculate the thermal effects because the thermal effects are attached with the pumping system of a laser crystal. So we can directly
okay,
calculate the thermal effect, thermal lensing, and then we can like I have a paper about this, work on it. We can like introduce these things, but before that, we need to understand the system. So that's why I'm not
okay,
sharing the paper's detail here.
okay, I understand. So basically, okay. So whether you start working on because it is necessary to use laser diode like in a stacked sequence, or we can use a just simple way. In ZMAX, you have a lot of flexibility somehow. So you
No,
either you use.
no. You can like have like stack lasers. It can be
Mhm,
horizontal stack because for the high power we use the stack lasers. Like
okay.
you can simulate with single bar. Okay.
Okay. Okay, I
It-
understand. So I can
yeah.
understand now it can be simulated. I don't think it will be a problem. We will see.
Sure.
But
That will be very nice.
I will require like if you can give me the parameter you whatever you have like the waveguide lens especially
Sure.
and then laser diode whatever information you have or if you don't have you can give me the model. I will see which
Sh-
information can I extract and then we will see how we can simulate it. I think
This
it
is
can
the
be
best
simulated in if we can simulate it in sequential mode that will be much better
non-sequential.
because it will give us a lot of flexibility to see vibration effects and
Uh-huh.
PSF, MTF, a lot of things. And the system which I am seeing here, I think I can simulate it in a sequential mode as well. So it will give us a lot more than what we want. But I will see when we start working on it.
Yes, sir, that will be very good of it if like it's possibly it can be simulated in a sequential mode, because like in sequential mode it's like for us it's a bit tricky, and like we see it's like the surface to surface propagation and these all things.
Yeah.
So that's why we never like go for sequential mode. We just directly use this optical system, the non-sequential, okay, component to component, and the ray tracing is like very simple here. So I
Yeah.
can share the non-sequential ZEMAX file as well, where I have shaped it as well. Okay.
Okay.
But there is like further optimization, and even maybe like at some point I am wrong about understanding each parameter where because
Yeah.
particular value belongs to which parameter. So there are
I
some
understand.
confusions there.
Yeah,
So we
so
can
Yeah.
we can
talk
make
about
it
this.
short a
We
bit.
can discuss.
Yeah, so we
Yeah,
can.
sure.
I-
This is a finisher.
Yeah.
Okay.
Yeah, but I will just say a few things that you can send me the file and the parameter, whatever you have. And if
Sure, sure.
the way you say you already some work, you found a paper like related to that, you can send me that as well. I will study that. And next meeting, I will
Definitely.
see how we can proceed with it. And
Uh,
maybe I can work on it according to my
Satyam,
according till that.
Yeah.
that's good. Satyam,
Mhm.
what are the form of like sharing? Like because like in my laptop I couldn't use the WhatsApp, so I have to like transfer to one place to another. So can we use
Email.
the email?
Email.
Yeah.
Yeah. I will provide you his email actually. I will provide you
Yeah,
his email.
basically because like in my I don't use WhatsApp in my laptop, so it directly cannot. I can send you on the WeChat as well if like
Yeah,
that is
no,
okay.
No,
I
email
can
is
share the email
fine.
address. I can share the email
Email
address.
is fine.
It's
Yeah,
not a
that's
problem.
okay.
Yeah.
Email will be like
Yeah.
better way to go.
Actually, I have so many questions, but to Mr. Fiaz, but I am not asking because lack of time. Otherwise,
Sir,
maybe some other day,
sir, I
if
am
you present some other day.
available at any time. You can like just send me a message. I
Yeah,
will
it's,
share.
it's okay.
Yeah.
Okay,
Now
so
you
Thank you,
will
sir.
see.
yeah, David, what do you want to say now?
Oh, okay.
Yeah.
Okay. Do you want I share my screen?
Yeah,
to-
sure. I mean,
Okay.
you can update us about the LIDAR or this kind of things. And you know that in the last meeting.
Oh, okay. I'm going to. Okay. Well, this meeting, I'm going to show how to modulate a flash LIDAR system on ANSI ZEMAX.
But you are supposed to, I mean, get some data or something like this. That was discussion with Mudassar or something like this. What was the discussion, Mudassar, last time?
So we just discussed, and he will just see for literature and see if we can simulate like a LIDAR system is optic based, not anything electronic or something is involved. So let's see what he gets, then
Okay.
we will see how to
Okay.
proceed.
Okay, start, David.
Okay. Firstly, flash LIDAR is the most simple LIDAR system because you only need to have a field of view or time of flight time. I mean that when you put a laser and then you
Can you share
get
your slide? You are sharing or something or not?
Yes, I'm sharing the screen. Do you know? See?
No, I cannot see.
We
I see
don't
you
see it.
only.
Okay, let me.
Yeah,
You
now
can
we
see the.
see it.
Yeah.
Okay. Let me. I'm going to introduce the flash LIDAR analysis on ANSI ZEMAX Optics Studio. Flash LIDAR is the most simple LIDAR system. Is when you have the goal is to illuminate the entire field of view with a single laser pulse and capture the time of flight from each illuminated point. To spread the laser light, you can use conventional diffraction grating. In this case, we are going to use the conventional diffraction gratings. They split the laser beam into a fixed pattern like a dot matrix, passive and efficient, but limited in dynamic control. There are newer ways to do that using meta-surface or grating made with metamaterials. There are nanostructure surface designed at sub-wavelength scales to modulate phase, amplitude, and duration of light. can generate complex light pattern from a single emitter made from material like silicon, TO, or plasmonic metals. In this case, the application of the flash LIDAR system, we are going to model the collimating optics. We have an array or source. In this case, we can use a BC cells array that is a array with diodes. In this case, these diodes are not visible to the human eye because they are infrared diodes. And then when you collimate this beam of the array, you pass to a diffractive element, and this diffractive element generate the matrix of dots. And in this case, for the illuminated area, we target 480 millimeters by 480 millimeters, roughly 19 inches by 19 inches in a meter away. In this case, this LIDAR is for thinking to use in the face of the user, like using the Face ID in the smartphones for unlock the device, or even to capture small objects in few meters away. For the illumination system, we can have some calculations for have the focal point. In this case, we are going to have 10 millimeters. In this case, for these results, we have the source half width divided by the collimator focal length equal to the central projection half width divided over the distance to the projection. To define the model in Optics Studio, the source was assumed to have a numerical aperture of 0.2 to 0.94 microns. The lens was optimized to yield a collimated output across the field of view to ensure that dots across the source array area were a reasonable size of the scene of interest. Due to the use case of the flash LIDAR system, it was also important to select a small form plastic material for a compact mass producible design. In this tutorial, the files was provided. I have all the files that the ZEMAX tutorial give me, but I don't simulate, only I understand how this system works. The next time I'm going to try to simulate
What
the
kind
files.
of file? Sorry, what kind of file do you have?
Yes, it's files dots say
Okay,
AR that are the ZEMAX files.
Okay, it's a ZEMAX file. Okay.
Okay, we have this lens systems that is the collimating beam. This is going to be the array of diode laser infrared, and we get to put all this with the collimation in a diffraction grating. And then we have passed to this system. We have this diffraction of the rays. We can do a geometrical image analysis and see if the spot is correctly or if they have some deviations. In this case, this is going to be our target system. We are going to try to avoid the zero order, because if focus all in the zero orders, we can offuse the sensor, because there is going to be a lot of light that can blind the sensor. So we need to try to work with the order 1 or order -1. The minus allowable diffraction angle, theta d, is therefore 2 times the horizontal half of view, with a focal C equal to 10 millimeters and the object height of 0.8 millimeters. The half view of the zero order is 4.57, which allowing use to require the system with the grating lengths in microns d. We can calculate the distance in microns of the grating is going to be 5.9 92 micrometers. Then we can simulate all these parameters in the ZEMAX, and we have the grating pattern. How does a special frequencies of 0.17 lines by microns means? We have this formula. We can have the frequency equal 1 divided by the distance, and we have if you have 0.17 lines by micron, we can have the original value. We have the 5.88 microns. And we can slightly difference due to using the angle that we are losing some decimals.
David, can I interrupt?
Yes.
Yeah. This file actually, did you make it, or is it already? I mean, you got it from them, or what exactly it is? This simulation. Did you do it, or what exactly?
No. It's a tutorial. I'm going to
A tutorial.
do this.
Okay.
Yes.
So,
And then we have this with the diffraction grating, and we have the freeze. We can see the yellow line is the zero order, but to try to avoid this zero order, we can move, in this case, a space line of 0.2 lines by micrometer, and we have seen less effect in the zero order of the diffraction grating. Then we can have the diagonal edge fly of view and the horizontal fly of view. We can also have a diagonal edge fly of view, or we can work with the horizontal or with the vertical half fly of view. And we use in this system a Koch triplet. That is, in this case, the design combines 3 lenses, 2 positive biconvex lenses and 1 negative biconvex lenses in the center, achieve aberration correction in a simple structure. We have here see the spot diagram in this case for different spot radius. And this case we can then compare it with the optical function, the model transfer function, and we can see in the red lines that is not diverged so much. So this system is well defined, even with allowing to get closer to the diffraction only system. We can start, because I was working on the sequential mode, we can start the conversion to non-sequential mode. In this case, we use the non-sequential mode in ZEMAX, and then we are going to work with 2 systems, the illumination mode and the imaging mode. We can combine these 2 modules, freeze the imaging mode, and then freeze the illumination mode, and then the imaging mode. And then we have here some consideration for do that. And the final details of the full assembly, we have these parameters. Then we have the Lambertian scattering profile. That is Lambertian profile is similar to the wood. And then we can simulate the reduce the ray intensity, this to avoid the sensor can be blind. And then we have the imaging module sensor detector and the scattering wall detector. Time of flight consideration, LIDAR system obtain the deep information of the scene by measuring the time of flight of light as it arrives on the detector.
David, can you
For
make
example,
a little bit brief? I mean, it's getting long. Can you make it a little bit brief?
Okay,
Sure.
okay.
Yeah.
For simulating the time of flight, we use the SOFS AP. That is a program that you can put some language like MATLAB, Python, C++, another type of language to simulate this time of flight. We have here the table, glass, and a ROM object that is going to be the hand of the user. We load the the source API to be simulating the time of flight. And then we have the distance. If you can see, you have different heights, because when the hand is more closer to you, to the LIDAR system, it's going to be more high. And the table that is more far away is going to be less in height. Then you can see clearly the hand, that this is the round object, the glass in the top of the table, and the table.
Okay, David, I mean, let's see if Mudassar can have some comments, because it will be getting longer. Okay, Mudassar.
What I want to ask, the LIDAR system, you just using that lenses and then you just all the you can say collimated beam or whatever on the diffraction, and you did that you can say diverge it and fall on the field of view. That depend on the distance, how much distance you want to take between the, you can say, the grating and the ground or detector. But my question is, how we can simulate this kind of system in, like you say, whether it is simulated like combining to like ZEMAX with the Python or something, or it is totally simulated in ZEMAX, because the object you have showing, or they will scatter the light back to the detector.
It's all simulated in ZEMAX, but for do the SOX API, you need to integrate a program language. You can use Python, or you can use another language. Okay, did you prepare for build the optic builder? In this case, we are going to translate this optical system simulation into the real world, incorporating a case. The optics builder, we import the CATS system. We cannot create the CATS system in ZEMAX. We use another program like SolidWorks or Katia or another type. And then we have, as you're seeing here, this is a wall that is going to be separating the illumination system of the LIDAR and the capture sensor of the system. We have with the OptiStudio simulation in the CAT platform simulation. And then we have the lenses, and we can surround these lenses with a barrel. And then we have the compact system. We can put and simulate again, and then have the case. This case we can simulate again with all the elements, but we have here some error that is being clipping. You can see that is when the system is not complete alignment. You have some disperfection, in this case, in this ROM. And you can try to then fix again with the CAT system to avoid this region. And then you can simulate again, and then you are going to have the rays passing well, like this final slide.
Okay, so it's mean we need to have a premium system for that, because the optics builder, and then you have to integrate with the Python. We need a premium version. It cannot be done.
Yes.
Mudassar, just a minute.
It's going to be with the premium version.
David, just a minute. Mudassar, I mean, this system, I made in a simple way. How do you see in a simple way? If you don't go to the premium.
Yeah, I can see it in a simple way. If we take the like illumination system from one end, then I put you can say like a mirror kind of field of view, then it is reflected from that, and then it will go to the detection system. That we can do in a, you can say, in a ZEMAX in a way. But I'm not sure whether it will it will be equivalent kind of system, but we have to try. But the way the actual LIDAR system acting, it will be difficult to, you can say, got the exact result. But we can kind of see some equivalent method for that. That is my point of view.
Yeah, I mean,
yes, we have all the files.
On ZEMAX, yeah, you can share the ZEMAX, all the files. I will check it, and then I will comment on it in more detail next time. I'm little bit getting tricky with that, whether how much we can do on a ZEMAX which we already have. So I will, after seeing the files, I will then tell you how we can proceed with it. Otherwise, it is a good thing. I just understand how to proceed, but there's a lot of things which maybe I don't know yet, or and we cannot do in our version. So we will see. how we can see that. How simply we can just using ZEMAX we can go far with this system.
Also, I have seen some
Okay, so
some
one thing,
models
just a minute,
and
just a minute,
okay,
David.
yeah.
One thing I
And
want to mention.
it is very low in
No,
cost. Is about
David,
$20.
David, just a
Okay.
minute, just a minute, just. Okay, so this meeting, I mean, when the time is gonna finish, so I will share another link because Nabil is going to present. Okay, so these meetings are more like a ZEMAX meetings now because he's also going to present the ZEMAX stuff. So okay, now David.
Yeah. Okay. We can also build the system. The BCL diode array is about $20.
You need to share.
Okay. Sure. For this case, we can simulate. This system is very small, but I have working with very small optics. This ray is not going to be visible. We need to use a thermal camera, or even with the smartphone, you can see the infrared light.
No, I mean, David, we have to be goal oriented. Okay.
Yeah.
What is the focus? What we are going to do? What we are supposed to do? This has to be so that we can have some results or something like this. So otherwise, I mean, if just sharing this kind of things, I think it's pretty useless. We need to focus what exactly we want to do.
Now, first
In our, I mean, with our limitations.
Yeah.
Okay.
That's my
yeah.
question.
This is
what we have already. We have to see what we can simulate using our ZEMAX, and then we have to look for things. We don't need like research work for that, but we have to first see which is optic based system, not electronic involved, so we can simulate in ZEMAX. That is my point of view. We have to see a LIDAR system in which we can, whether it is a simple or complex one, we have to take a LIDAR system which is the optic based, and then we have to see how we can simulate in our ZEMAX. Later on, whatever the people can do like optics builder or with the integration with Python, we will see that later once we have at least basic idea in ZEMAX, so we then can see these things. I think
Okay.
so, because ZEMAX we don't have a premium, so it is no use to see how we can integrate it with the Python or other thing. I think for timing it doesn't give me any idea to proceed. So we have to see something straight which we can do. That is
okay. Yeah. Also, the tutorial they don't do the stop analysis, the thermo optical stress analysis.
Okay, Nabil, do you have any comments about it? What David presented here, Nabil.
Nabil is here.
Yes, Nabil. Nabil, can you hear me?
There's around 2 minutes left. So
yeah, I will share the link. Okay, so you people, I will share the link with the.
Can you hear me?
Yes.
Yeah.
You have two. Actually, you are online from two computers. Nabil computer and Nabil
yes, sir.
mobile. Okay, say what comments?
Yes, sir.
Yeah. David, I mean, what about the David stuff?
Actually,
I mean,
sir, what actually the thing is that the concept is not very much clear to me right now.
Okay.
I mean, actually, I have to go through the file. At least this ZEMAX file which we were sharing in his slide.
Okay, let's stop it here, and I will share the other link now. Okay, all of you. Then you can have your presentation. Okay.
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 Okay.